Hello, welcome back to another day of whatever this thing is that we're doing together. I believe it's called math. All right, let's do some math. Let's go. So, we are solving systems of linear equations today. This is something that you have definitely done before in a regular old algebra course, probably in high school. But we are going to expand the toolkit and give you better ways to deal with these classes of problems. So, in case you have forgotten what these things look like because it's been a minute, here they are. Now, it can be any number of variables, it can be any number of equations, and we are going to have our variables x, y, z, or, x1, x2, x3, and we'll have a bunch of coefficients. And this linear combination of the variables is the set of equations that we are working with. But rather than doing the stuff that you have learned in the past about, oh, okay, does do substitution and isolate one variable and then plug it in the other equations and then eliminate things, and like that works, but there's a faster way. And the purpose of this day's worth of content is to give you those faster ways. And they involve matrices. So the two methods are, the one we'll look at today is dealing with matrix inversion. A lot of people asked about inverses and just more about what is that and what does it mean and how are determinants involved and all that. So we're going to unpack that. And the great thing about solving systems of equations by inverting matrices is that you don't need to be creative. There's a recipe, you follow it, and at the end of the recipe, you get your answer. And if the matrix is invertible, then you're golden from there. It will always work as long as it's possible to invert the matrix of coefficients. On the other hand, inverting matrices is very computationally intensive. So when you are considering this as a strategy for solving your problem, the bigger the problem is, the more painful this method is going to be. And if you have a matrix that is not invertible, we'll look at what the implications are for whether a matrix can or cannot be inverted and what conditions that occurs under. Then if there is no inverse, then obviously using the inverse does not work. The other approach, which we'll see in the next video, is called Gaussian elimination, which is basically a nicer way of doing the stuff that you probably learned in your high school algebra class. It's just faster, more efficient, nicer notation. It is very simple computationally. All you have to do is additions and multiplications. Like, that's really it. And it always works. So Gaussian elimination is nice, but it does require to use your brain a bit because there's not just a fixed recipe that doesn't require any sort of planning or decision making in it. Okay, so for writing this stuff down and for talking about these things, the equation that I showed on the first slide, or the set of equations, really can be written as the form of matrix times vector equals vector. This is a form of equation we will see a lot in the next few weeks. This basic form can describe a wide variety of different classes of problems that all can be unified by this way of notating numbers multiplied and added together. What the content of this matrix and these vectors are, the A1, A2, A3, so on, those are the coefficients of the variables in these equations. And then the x vector is the variables themselves, so the x, y, z, or x1, x2, x3. And then this b vector is the homogeneous or inhomogeneous terms. I mean, that's the fancy math name for these things. But if the right-hand side is 0, they are called homogeneous equations. If the right-hand side is not 0, they are called inhomogeneous equations. This is just naming. We want names to give things so that we know how to refer to them. At the end of the day, either your linear combination of variables adds up to 0 or it adds up to not 0. And the reason for making that distinction is it does influence which strategies you're going to use to solve the equations for your variables. But looking at this as matrix multiplication for a second, if you relate it back to what was on the first slide, you can see, oh, this kind of looks like a matrix multiplication thing now that you've done a little practice with that. right? That's a column of the matrix. And that's a column of the matrix. And that's a column of the matrix. This A, E, J, B, F, K business, that's your coefficient matrix. This is your homogeneous or inhomogeneous vector on the right-hand side. So like, yeah, okay, this starts to actually look like doing matrix stuff when you see A times X plus B times Y plus C times Z is A times X plus B times Y plus C times Z, right? That's the dot product of the first row of the matrix and the column of the vector that you're multiplying by, which that's matrix multiplication. So already we're using this notation to condense things and just write less stuff, which is already a benefit. But it gets better. It gets better. Now, I've invoked high school algebra a couple times. Let me remind you of a couple other things from high school algebra, which is when you have a system of equations, there are three possible outcomes for that system of equations. One is that there's a unique solution, that there is one value for X, one value for Y, one value for Z or Z to any Canadians in the room. And that's it, and you're done, and it's great. This is nice. That's not always the case, however. Sometimes there is no solution to those system of equations. And thinking about it geometrically, if each of those equations is like a line or a plane, that's saying that there's no intersection of those lines and planes, that there's no point where they all meet each other. And that happens sometimes. But there's also the possibility of infinitely many solutions, that there are infinitely many values of X and Y and Z that all satisfy the initial equations. And in that case, you will freely choose one of the variables, or maybe more than one of the variables, and the values of the others will be determined by that free choice. So the ratios of the variables to each other are fixed, but the absolute values of each variable will not be fixed. Okay, so these are our possibility spaces of what might come out of solving this. Looking at systems that have unique solutions, and if you're like, but how do I know if there's a unique solution? We're getting there. But let's start with this case. If you have a square matrix, so that means we have the same number of variables and equations, and if the determinant of the coefficient matrix is not zero, then we will have a unique solution. So this is one of the, honestly, the best tools that you have for determining whether there is a unique solution. Square matrix, non-zero determinant, inhomogeneous. If those three criteria are met, you definitely have a unique solution. Now, in other cases, it may be possible for a unique solution to exist as well, but there are additional conditions that you would have to get into in those cases to know for sure. You can also just sit down and solve the thing and see what happens. But on the focus of this particular video, in this case, for this set of problems, square matrix, non-zero determinant, inhomogeneous system, all you need to do is invert the matrix, and that gives you the solution to the set of equations. So you write down your coefficient matrix, you invert it, bam, you're done. And you're like, okay, cool, thanks. I guess that helps, except you never told us how to invert matrices. And then, well, yeah, you're right. I didn't tell you how to invert matrices. Maybe we should address that. Maybe this is the right time to tell you how to invert matrices. And yes, that's exactly where we're going with this. I do just want to repeat that computationally, matrix inversion does not scale well. For small matrices, 2, 3, 4, whatever, yeah, of course, it's no big deal. But when your matrices are million by million or larger, this gets very painful very quickly, and you will usually want to use a different set of tools for solving than matrix inversion. But how do we find the inverse of the matrix? I've been teasing this for a couple days now. We should actually go ahead and do it. First thing you want to do is to test whether the matrix can be inverted. Save yourself the pain of trying to go through the math just to realize that there's a problem later. First thing first, matrix must be square. Non-square matrices do not have inverses. And that's because the condition for matrix multiplication, remember there's this rule about number of rows and number of columns in the matrices. If you were to try to take a matrix, a non-square matrix, and multiply it by some version of itself, then you wouldn't even be able to do that multiplication. And remember, the matrix inverse is the matrix that you multiply a matrix by its inverse, you get the identity matrix. That's the definition. So if you can't do the matrix multiplication, then it can't possibly be the inverse. Okay, next check. Zero determinant means no inverse. Why that is, we will see in this video, coming very soon. But if those two conditions are taken care of, you're good to go. If it's square with a non-zero determinant, it is invertible. And then, in that case, we proceed with actually doing the matrix inverse. Why have I been putting this off so long? Because it's a pain. Inverting matrices, there are so many different approaches to this problem. Secretly, not secretly, I'm saying it out loud. I believe it's because everyone hates inverting matrices, and mathematicians were like, maybe there's a good way. Maybe if we try enough ways, we'll finally find the good one. They all suck. Some are worse than others, but it is what it is. It's so bad that there's a whole page on Wikipedia just giving a list of all the different ways that you have options for inverting a matrix. Good news is this is a problem that is so well suited for computers. I know I said it takes a lot of computing power just in terms of the raw number of calculations, but it is very formulaic, and it is addition and multiplication and division and subtraction. So it's very much the kind of task that is well suited to doing on computers. I'm going to teach you 2x2s today, and I do want you to be able to invert 2x2s by hand, because two variable, two equation systems are actually pretty common. Think about binary alloys. Think about any mixture of two components that you're making a material out of two things combined in some proportion. Like, that's a pretty common thing in real the real physical universe we inhabit. So anyway, we're gonna do 2x2s by hand. Bigger than that, if you want to go learn about it, great. I'm fully in support of going and learning more things, but I will not require you to do bigger than a 2x2 matrix by hand in terms of inverting matrices. So let's work it out. What is this thing? What is the process? Well, remember, we are using these matrix operations to represent systems of equations. Here's my 2x2. This is an inhomogeneous equation. You can see that I have some coefficients, or not coefficients, but some constants, L and M, on the right. And I have AX plus BY equals L, and I have CX plus DY equals M. What we need to find is the matrix that, when we left multiply it by this whole system, we're looking for the numbers E, F, G, and H. What are they? We're looking for those numbers that, when we multiply the matrix EFGH times the matrix ABCD, the result is just 1. Really, it's the identity matrix. So that on the left-hand side, the only thing that remains is X and Y, which is what we're trying to solve for the values of the variables. And that means that the solution to this set of equations will be the inverse of ABCD times the inhomogeneous vector LM. Which means that in order to know what the inverse of a 2x2 matrix is, if we solve these equations for X and Y, then the coefficients that we get will be the elements of the matrix inverse. Let's do it. Here's our equations. And again, I really encourage you when you're looking at this written down, see it in the form of the matrix structure. This will help with your visualization of what is happening in the process of matrix multiplication, matrix and vector multiplication. So we have A, B, C, D. Those are the coefficients. That's the coefficient matrix. We have X and Y for our variables. We have L and M for the inhomogeneous terms. Well, let's solve for X. I heard that's what people do in math is solve for X. You know how to do algebra at this point, so I'm not going to talk through like every little step, but we solve for X. Here's what we get. You subtract, you divide. And now you can substitute that into your other equation. So here it is, C times X, where X is the thing we solved for, plus D times Y equals M. And now I am going to keep going, and I will solve this for Y. So to get rid of fractions, because fractions are the enemy, we're going to multiply everything by A to cancel out that denominator, and then collect like terms, factor out the coefficients from the Y's. And so when you do this multiply by A, collect like terms, factor, we have this expression with that dA minus BC multiplied by Y. And we have the force on the right. No, that was just a joke. I was not serious. It's just the number M times the number A. It's not mass and acceleration. That was an accident. Um, sorry, physics brain. Can't be helped. Anyway, we subtract, we divide, and we solve for Y. This is the value of Y. Y is this combination of constant terms. But look at the bottom. I also rearranged things to be in more or less alphabetical order. Look at the bottom. AD minus BC. Go back to the coefficient matrix. AD, forward diagonal, minus BC, backward diagonal. It's a thing. It's a thing that maybe you recognize because it was in the last video. It's the determinant. And this is where the determinant starts to show up for the first time, not for the last time, as a useful quantity that helps us calculate and understand other things. The determinant is the thing that we divide by, the scalar number that we divide by when inverting a matrix. And so when I made this comment in the last video about the determinant's kind of like the total size of the matrix in a way, well, if inverting a matrix is our analogous operation to division, then it would make sense that multiplying by the inverse should involve dividing by a number that's kind of like the size of the matrix, which is kind of like what the determinant is. These things are not exactly mathematically rigorous statements, but they are very good analogies, and I think they're genuinely helpful conceptual tools, which is why I do keep bringing them up. This also tells you why you have to have a non-zero determinant in order to invert a matrix, because we're dividing by the determinant. So if the determinant is 0, dividing by that is a bad thing. Like, capital B, capital T, bad thing, according to the rules of math people. Okay, so here's our first application of the determinant. It is an ingredient in inverting matrices, and it is a quantity that tells us whether a system of equations is uniquely solvable, whether that system of equations can be inverted to give the variables in terms of the coefficients in a fixed single form with a unique solution. So just collecting and rearranging the terms. I'm not writing out the algebra here. It's algebra. It's multiplying and dividing and subtracting. But when you collect things and when you factor, here's what you end up with. And this gives us now the formula for the inverse of our coefficient matrix. This is the inverse of a 2 by 2 matrix. Here it is. Bam. This is the one inverse formula that I'm saying, please go ahead and memorize this. I generally don't make a big deal out of memorizing a lot of formulas. I much prefer people to understand patterns and reasons and concepts, formulas you can always look up. This one is simple. It's not too bad. It reinforces that divide by determinant factor, which I've made a big deal out of. And looking at the top of the matrix, you're like, that looks kind of like ABCD, but it's just sort of shuffled around, like we did some rearranging. And that's a good perception. When we find the inverse of a matrix, we essentially rearrange the elements according to certain magical rules that also involve a lot of minus signs, and then we divide by the determinant. That is true for matrices of all sizes. It's just that as you get to bigger and bigger matrices, it's more painful to do the math. But that concept, rearrange elements, put minus signs in the right places, divide by the determinant, that is the general process conceptually for inverting a matrix. Now, I said that there's a bunch of options and they all suck, and that's true. I stand by it. There is one that, in my opinion, is the least painful one, and it's a really nice example of the process in the next video, so I will bring that up when we get there. But just as I said a minute ago, we rearrange, negate certain elements. Those patterns, if you're interested, if you're curious, go look it up. It's actually pretty neat from just a seeing patterns in math point of view. If you're the kind of person who likes rules and patterns, it's a fun time. Um, but again, not going to require you to memorize or do by hand those larger formulas. At the end of the day, though, this is a great way to solve systems of equations. You write your coefficient matrix, you invert your coefficient matrix, and then your answer is literally just inverse matrix times inhomogeneous vector, and that gives you your vector of solutions, and you're done. Like, that's the whole thing. So at the end of the day, even though finding the inverse is a bit of a pain, it gives you a really nice way to approach these problems. And that's all I have to say about that. I'll see you in the next one.